Hello everyone, it's Kayla, your tutor for Anthropology 102 with Dr. Scott Suarez. I wanted to make a quick video on our Hardy-Weinberg Equilibrium problem set on Canvas. So in case you find yourself having some trouble with it and you're unable to make it to my session, or you just want to walk through it together again, you can look back at this video on your own time to get some guidance for what to do with these kind of problems. So I'm using the same problem set from Canvas, but I did add in this table that we saw in lecture, which I think is pretty helpful for just figuring out where to start. So this table shows us we have 3 possible genotypes we're working with. Typically, we have 2 homozygous genotypes, so those are the ones that have 2 of the same allele. So for example, AA and BB, those are the homozygous genotypes, which means AB, the one in between those, is our heterozygous genotype. Okay, and then we can see how those alleles sort out. And then we have these equations, or the probabilities, on the right column. These are going to be important. These are what we're using to solve these problems. So we'll see those in play in just a moment. I also have written down here the probability of each genotype. Added up, they should all equal 100%. So if you add up p squared, which is this probability here, plus 2pq, the probability of the heterozygous genotype, as well as this one, it should all equal 1. And we'll do a couple of checks, which I always suggest people do just to make sure you're doing the math right. So let's just look at problem 1 here. It says, suppose for a moment that a primatologist knows that in a breeding population of ring-tailed lemurs in a forest of Madagascar, the frequency of the A allele is 0.8 and the frequency of the B allele is 0.2. So you can see I've highlighted those points. A allele is 0.8, B allele is 0.2. These are the numbers we're going to be using, plugging into these equations. So the first thing we're going to want to do is, in space A for each of those, we're going to write the frequencies of those genotypes. So we need to find the frequency of the AA genotype, the homozygous, the frequency of the heterozygous AB, and the frequency of the homozygous BB. Alright, so we're not going to worry about the second part yet. Let's just focus on the first part. So we're told that the A allele frequency is 0.8, B allele frequency 0.2. One thing you should notice is that that's also always going to add up to 1. So 0.8 plus 0.2 equals 1. So we're going to be using these equations up here. I like to start with the homozygous genotypes, so AA and BB. We see that their equations are over here. P times P, which is P squared, and Q times Q, which is Q squared. So the first thing you're going to want to know is that when you see P's and Q's, we basically write it like this. The A allele frequency, 0.8, that's going to equal P. Okay, and then the same thing for the B allele frequency, 0.2, that equals Q. Okay, so now all we have to do to find these genotype frequencies of AA and BB, we're just plugging in those equations. So for AA, our probability equation was P squared. So we're plugging in 0.8 squared. And if you plug that into your calculator, you should get 0.64. You could also write this as 64%, if you like to think of it in percentages. Okay, so that would be A. I'm just going to write 0.64 because we're going to do something with that number in just a moment. So the next one I like to do is the other homozygous genotype, which it's the same process. We're just squaring Q, which is the same as the B allele frequency. So we're plugging in 0.2 squared. If you plug that into your calculator, should get 0.04 or 4%. Okay, so I'm just going to write down here 0.04. Alright, so we already found 2 of those genotype frequencies. The last one we want to find is the frequency of the heterozygous genotype, AB. So that equation is going to be a little bit different. If we look at our chart up here, AB, there's 2 ways, basically, that you can get that genotype, right? You can get an A from mom and a B from dad, or vice versa, B from mom, A from dad. So because of that, we have to do 2 times P times Q, because each of those instances is P times Q. And because there's 2 ways of getting it, we're just multiplying that by 2. So again, we're using the same numbers, but the equation's a little bit different. AB equals 2PQ. So we're doing 2 times frequency of the A allele, which was 0.8, times the frequency of the B allele, 0.2. And if you multiply that, you should get 0.32 or 32%. 0.32. One thing I like to do at this point is add up those numbers, because it should equal 1 or 100%. So if you add up 0.64 plus 0.32 plus 0.04, it should equal 1. And if it does, you know you've done your math right. If it's a little bit off, that's okay. Sometimes we might get like 0.1 or so over. As long as it's close to 1 or 100%, you probably did it right. Okay, so that's part A of the problem done. Part B says, write how many lemurs of each genotype you would expect if there were a total of 500 lemurs in the population. So just think for a moment, how do you think we would find that number? Well, these are frequencies or probabilities or percentages, right? So if we want to find 64% of the population, we could just multiply the genotype frequency by the population number that's given to us, which is 500. So, for the total number of homozygous AA individuals or lemurs in the population, we're going to do 0.64 times 500. So we're going to get 320. Right? And in case you don't know how to do that, again, we're just multiplying 0.64 times 500. It's 320. Then we just do the same for the rest of them. AB, 0.32, so it's 32% of the population of 500. If you do that in your calculator, you should get 160. And then the last one, same thing, 0.04 times 500 is 20. So one thing I will point out here is make sure you're using the decimals when you're doing this calculation. If you were to multiply 64 by 500, you would get a number that's not correct. So you want to be using it in the decimal format of the percentages. So let's just fill that in. So this is just saying that in a population size of 500 lemurs, we would expect to find 320 of them have the AA genotype, 160 of them have the AB genotype, and only 20 of them have the BB genotype. And again, we could check if we wanted to check our math. If you add these numbers up, it should equal 500. Okay, so that's problem 1 done. So problem 2 is a little bit trickier. It says that, now suppose that in a population of star-bellied sneeches, you knew that the number of individuals of the 3 genotypes, yes, sneeches are known to carry many of the same alleles as lemurs. Given the following values, we want to find the frequency of the A allele and the frequency of the B allele. So there's a couple ways you could start a problem like this. The first thing that I like to do is find out what the total population size is. So I just add up 6,561 plus 3,078 plus 361. So if we just do that real quick, 6,561, oops, 61 plus 3,078 plus 361, we get a total population size of 10,000. So what good does that do us? Well, the problem is asking us to find the frequency of both the A allele and the B allele. And we know that each individual in the population has 2 alleles, right? Because you either have AA, AB, or BB. So each of these 10,000 sneeches is going to have 2 alleles, which means that if we do 10,000 times 2 for each allele, we have a total of 20,000 alleles. So 20,000 total alleles in the whole population. Alright, so that number is going to be important when we're dealing with frequencies of alleles. So we'll just set that number aside for now. The next thing we want to do is figure out how many A's of those 20,000, how many of them are A's, and of those 20,000, how many of them are B's. Okay? So we're going to take, let's just start with the number of AA individuals. We have, in that AA genotype, there are 6,561 individuals, and all 6,561 of them have 2 A's, right? So we're just focusing on how many A's do we have. So right off the bat, we have to multiply the population of AA genotype by 2, because each one of those has 2 A's. Okay, so you should get 13,122. But we're not done yet. Right, we still have to figure out how many A's are in the AB genotype, right? Because they have A's as well. The AB heterozygous genotype is easier. We don't have to multiply it by anything, because each AB individual has 1 A. They also have 1 B. So we're just going to add this number onto what we just calculated. So we have 13,122 A's from the AA genotype, plus 3,078 A's from the AB genotype. So I'm just going to label this. This is from AA, and this is from AB. So 3,000 more A's added onto that. And if you add those numbers up, you should get 16,200 A's. Okay? So let's find B, and then we'll finish finding the frequencies of those. So again, I like to just start by finding how many Bs we have in the homozygous population. We have 361 individuals with the genotype BB. So 361 times 2, right? Because each one of those individuals has 2 Bs. That's going to give us 722. And then again, we have to add 3078 because you can't forget that heterozygous genotype. So this is from the BB population, which we multiplied by 2. This is from the AB population. So again, we add those numbers up, and you get 3,800 Bs. Okay. So we found the total number of A's and the total number of B's in the population, but we're not done yet. In order to find the frequency of those, we now have to divide those numbers by the total number of alleles. Right? We're trying to find that percentage again. So, 16,200 divided by 20,000, because remember that we calculated earlier that there's 10,000 individuals in the population. Each one of those individuals has 2 alleles, so our total allele count is 20,000. So this is the A frequency. So 16,200 divided by 20,000 is going to give you 0.81, or 81%, you could write. And then we do the same thing for B. We said we have 3,800 B alleles out of 20,000 total alleles. And if you punch that into the calculator, you should get 0.19, or 19%. Again, you can probably tell these percentages, 81 and 19, add up to 100, which is what we like to see, so we probably did our math right. So we can just write in here the frequency of the A allele is going to be 0.81. Frequency of the B allele is 0.19. Okay? So that's how you find the allele frequencies. Alright. We're almost done. So, question 3 is very similar to what we did in question 1. It gives us our allele frequencies of A and B, asks us to find the frequency of the genotypes, and then in part B, it gives us a population number of 1,000, and we have to write the number of each genotype in part B. So I'm going to leave that one up to you guys. It's the same process, again, as you do in question 1. So if you need help with it, you can rewind and go look at what we did in part 1. But you're using the same equations, so you're going to use p squared to find the frequency of the AA genotype. I'll just write the equations in here. So you're going to use p squared here. You're going to use 2pq to find the AB genotype frequency, and you're going to use q squared to find the BB. And remember that this A allele is P, this B allele is Q. Okay, so you should be able to figure that out. And then, for part B, you're just going to take that number and you're going to multiply it by 1,000, right? Because that's our population size. So whatever you get in A, it's basically going to be like this number times 1,000. So this, you could say AA times 1000 AB times 1000 and BB times 1000. Okay? So it says the third wish is even harder. The genie suggests that the A allele is dominant to the B allele. We want to know how many of each phenotype would be expected in a population of 1,000 individuals. Alright, so the key here, it tells us that A is dominant to B. So we're going to have two possible phenotypes. So what I like to do is just sort them. So our phenotypes, remember that phenotype is the outward appearance of the genotype. So we had three genotypes. We had AA, AB, and BB. But because it says that A is dominant to B, that means that any genotype that has an A, we're going to add those up, because that's going to be one phenotype. So AA plus AB. And then the other phenotype we have was BB. So whatever numbers you get from this previous problem here, the numbers that you get in part B, you're just going to add those up. Okay, so that's all you have to do for that part. And you might get like some decimals in those answers, which is okay. And then lastly, this problem says, your professor does not have the power to grant any wishes, but will be very impressed if you can answer the following conundrum. If you sampled 1,000 individuals from the population that the genie was talking about and discovered the following numbers, what reason could you suggest for the deviation from the expected numbers? So I'm going to let you guys think about this one on your own again. I can give you a little hint though. If you recall why we use Hardy-Weinberg Equilibrium, so HWE, the whole purpose of using these equations is to detect the presence of evolutionary forces. Alright, so the problem is saying that these numbers that we found are not the numbers that we expected. So the expected numbers are what we calculated, basically. So anytime the actual outcome is different from your calculation, it means one of those forces of evolution is at play, is happening in that population. At least one of them. It could be multiple, but at least one of them has to be occurring. So if you can remember what those 5 forces were, forces of evolution, that's going to explain why these numbers are different than what we expected. So see if you can remember what those 5 were. You may have to go back through the lecture slides or through your notes. But these are really important, especially to Hardy-Weinberg Equilibrium. So if you're not familiar with them, I suggest going back and reviewing. And again, if you have any questions about that problem or any problem on this worksheet, don't hesitate to email me. I know the answer key to this is on Canvas already, but I just wanted to make this to kind of help you guys walk you through the process if you needed an extra hand. So yeah, best of luck, and I hope to see you in my sessions.